After we get through the diagonalization process, which involves the eigenvalues and eigenvectors, we can take a look at how these things, how you can have a matrix similar to another matrix that looks like a diagonal. Okay, I'll start with the definition of similar. A matrix A is similar to B if there's an invertible n by n matrix such that the inverse of that matrix times A times P, the actual matrix P is equal to B. Now, initially when it's defined, it is important where the P inverse and P are located, because this is saying that A is similar to B if you can transform A to make it look like B. But in our next theorem, we'll see that the order isn't going to matter, because you remember the properties of equality. There's transitivity. It's transitive? Reflective, sorry. It's reflective, which means A is equal to itself, or in this case, when we're talking about similar, A is similar to itself. It's symmetric. Symmetric to say if A is similar to B, then B is similar to A. And then it's transitive to say that if A is similar to B and B is similar to C, then A is similar to C. So that whole idea about the reflective, symmetric, and transitive was some information that we got from, or those are some basic rules that were stressed in some lower level math that we may have forgotten about at some point. But they do this stuff in geometry when they talk about congruence and stuff like that. Congruence is also one of those that's reflective, symmetric, and stuff. I've been trying to avoid proving things in the class, but I think these are really simple and easy to do. So let's see if we can prove these things. So we'll use a definition of similar to prove this, and to try to prove that A is similar to itself, what we need to do is we need an invertible matrix to multiply with A on the inverse on the left and then the actual matrix on the right, so that you're going to get the matrix A. And what would that invertible matrix be? Any guesses? The identities, regardless what size we're talking about, if we get the identity inverse, which is the same thing as itself, times the identity, then this checks out, and so that's how you would prove the first one. For the second one, the if part is something that we get to assume, so we're going to assume that A is similar to B. So if A is similar to B according to the definition, then there exists a P inverse A, P, so that if you multiply these things, you get B. Now, if this exists, what we want is a couple of matrices, invertible matrix, inverse in its original matrix form, to multiply with B on the left and on the right to get A. And what would that be? It would be, well, it would be P inverse inverse, which is just P, but we'll write P inverse inverse and then P inverse. And so if we do this, we should get A back, and then we can go through a little bit of a proof to show that this is actually going to work. And then the last one, we can assume a couple of invertible matrices. Let's say P, one of them is P, and let's say the other one is Q or something. So A is similar to B means we can have a P inverse A P equal to B, and B is similar to C. That means we can have another matrix that might have nothing to do with P, so let's call it Q inverse B Q, and that's equal to C. And then transitivity says that A is similar to C, so we want, I guess this should have been in, not like should be blue. And so what we want is a relationship between A and C. So if we can find a matrix here, and I drew the boxes bigger because it might be bigger, so that this is going to equal to C. What do you think that's going to be? This one's more of a stretch to try to think it through, so maybe we can just use this information that we got. So why don't we have a relationship between A and B and then B and C. So why don't we take B and put that in there. So we have Q inverse, and then the B we're going to replace with P inverse AP times Q, and this is supposed to equal to C. So you see that substitution that we did? We just replaced B with what we knew from before, and then since matrix multiplication is associative, we can regroup and call this Q inverse P inverse A, and then PQ is equal to C. So the invertible matrix that we're looking for in this case would be PQ, and then the inverse of PQ is Q inverse P inverse. So that would be the matrix that that we would be looking for. Okay, so these are simple one-line proofs, I guess, if you can call this one line. Simple one-line proofs that show you the symmetric, the reflexive, symmetric, and transitive properties of this similar matrices. Okay, good? All right. So that just allows us a little bit of freedom now to say when things are similar to each other, then we can find relationships like this. All right, what else is special about similar matrices? It turns out that there's a lot of things in similar matrices that are important for us. And that involves this theorem. Next theorem. So these set of inequalities is going to be a little bit more challenging, a little bit more difficult to prove. Maybe we'll just prove the first one and see what happens after that. But in any case, we have A and B being similar. It turns out that there's a lot of important properties that follow. So if A and B are similar, then the determinants are equal. So that's a pretty big deal, determinants being equal to each other. If A is invertible, then B is also invertible and vice versa. Of course, if A is invertible, it follows that a determinant is non-zero. So then the B determinant is also non-zero. So that kind of follows directly from A. A and B have the same rank. That's also another important aspect of having similar rank matrices. And then the other two that are really important are that they have the same characteristic polynomial. Now that is seems to be more information, more powerful than the others, and then they also have the same eigenvalues. And the fact that they have the same eigenvalues is going to be our leading up to being able to what's called diagonalize the matrix. So we're going to want to be able to diagonalize the matrix. All right. So let's try to prove the first one. I think if we prove the first one, the second one follows, and we can say that we kind of proved 2 out of the 5. So let's see if we can prove the first one. The determinant of A is equal to the determinant of B if the two things are similar. So we assume that A and B are similar. So we'll assume that A is similar to B. That implies, according to the definition, that that there exists an invertible matrix P, so that P inverse A times P is equal to B. So let's see. That means we're interested in finding the determinant of, let's say we know the determinant of A. Let's find the determinant of B. So the determinant of B is equal to the determinant of P inverse AP. But then there was a rule about determinants saying the determinant of a product of matrices is the determinant of each of those matrices multiplied together. So this is equal to determinant of P inverse times determinant of A times determinant of P. And then now there's another rule about determinants that says the determinant of an inverse of a matrix is 1 over the determinant of that matrix. So that pretty much finishes up our proof here, because you would be able to cancel the first and last terms, and then all you have left is the determinant of A. So the determinant of B is equal to the determinant of A, which is what we were trying to prove. So that's it. And next one, if it's invertible, then if and only if A is invertible, if and only if B is invertible. So if we show that if A is non-zero, the determinant is non-zero, then because we know that the determinant is 0, if it's invertible, the determinant is not equal to 0. So that kind of follows. And then the rank into characteristic polynomial is a little bit more involved, so we won't prove that. Okay. But now we have a list of facts that we can use to exploit when we're studying more similar matrices. All right, let's go to the next. I was going to try to do some examples, but I realized I didn't pull out any examples to check if two matrices are similar. So let's just go past that and go jump into diagonalization, diagonalizable, diagonal. So here's our next important theorem or definition. If an n by n matrix A, well, not if, an n by n matrix A is diagonalizable if there is a diagonal matrix D such that A is similar to D. So remember that D is if you have a diagonal matrix, then your D is going to look like this. It's a bunch of things in a diagonal and zeros everywhere else. Okay? So the numbers here in the diagonal must be special, right, with respect to A. This is coming from A. So what would you guess, based on the theorems that we were looking at earlier, what would you guess would be the elements in the diagonal of the matrix that you're looking for? So take a look at the last two, A and B. If A is similar to B, then A and B have the same characteristic polynomials, and A and B have the same eigenvalues. So do you remember something about the diagonal matrix and what's special about the diagonal matrix? The determinant. So the product of the diagonals is exactly the determinant. What else? Yeah, determinant is 0. It's not, yeah, so we won't worry about that. Something else about the diagonal. Their eigenvalues. If you have a diagonal matrix, then the entries in the diagonal are exactly your eigenvalues.
Right, but isn't that because
No.
that's how we were finding the characteristic equation?
That's for A. Oh, yeah, something equaling 0. That's how you find the things. But in this diagonal, or in finding this diagonal, so if you have a matrix A, and you want to know if it's diagonalizable, or if you know it's diagonalizable, you want to know its diagonal matrix form, then all you need to do is look at the eigenvalues. So the diagonals, elements in the diagonal of D are eigenvalues. So if you're given A and you want to find out if it's diagonalizable, and or if you want to find out the diagonal matrix that's similar to that, all you have to do is find the eigenvalues of A. So it turns out that finding eigenvalues of A will lead to the diagonals. Yeah. And then the number of diagonals need to equal n. So even if you have repeating eigenvalues, the algebraic multiplicity has to be the same as the geometric multiplicity. So if you have a lambda minus 1, or if lambda minus 1 to the second power, or if lambda has algebraic multiplicity of 2, then when you find its eigenvectors, you hope to have 2 eigenvectors associated with that. All right, so our key to finding the diagonal is to figure out what the eigenvalues of A are equal to. So that's not the whole story yet, but let's see. Let's just pick one of these matrices. Let's pick number 10 maybe as an example. Is this easy? Oh, it's an upper triangular, so. Okay. All right. So let's find the eigenvalues of this. You need to subtract it from lambda I. So A minus lambda I, and then you get your characteristic polynomial, or you want the determinant of this. So A minus lambda I to 0, 0, 1 minus lambda And since this is an upper triangular matrix, it turns out that, you know, your characteristic polynomial is just going to be that. So that's nice because we don't have to worry about factoring. It's already factored for us. And so we can immediately find our eigenvalues. So our e-values is lambda is equal to 1. This has multiplicity 2. That said 1. This has multiplicity 2. So let's call it algebraic multiplicity 2. And lambda is equal to 2 is our other eigenvalue. So for each of these, we want to figure out our eigenspace or our eigenvectors. But in any case, before we do that, before we jump into eigenvectors, because we now know that this is our eigenvalues, then we can have a matrix D with these eigenvalues. So 1, and then 1, and then 2, and then zeros everywhere else. So this is your diagonal matrix that this is similar to. So A and D are similar.
Is that true only if?
Oh yeah, only if.
Find two eigenvalues.
Yeah.
For one.
Only if lambda is equal to 1 is has geometric multiplicity of 2. Yeah. If it was 3 different distinct eigenvalues, that's even better. It's easier to deal with. But since this is repeating, we still have to hold out for hope that the eigenvalue of 1 has 2 eigenvectors associated with it. The order of the rows, let's say the order of the columns, or the order of how you lay out your eigenvalues.
Yeah, what if we drew diagonal 2, 0, 0, 0, 1, 0, 0, 0?
This also, given the same condition, if this is the same geometric multiplicity, then this should also work. So to answer your question, does the order of the eigenvalues matter? No, it doesn't matter to find our diagonal matrix, but it will matter because to show that this is actually going to work, we probably should find P, right? That invertible matrix that switches off. So it will matter when it comes to finding that matrix P. So either one of these, let's call this D1 and D2. D1 and D2 should work. I'll say should because we still have to check to make sure that, you know, the eigenvalues or eigenvectors are going to work for us. Let's actually check it to make sure that this does work. So let's find the eigenvectors for lambda is equal to 1. And we might as well find it for lambda is equal to 2 as well. All right, let's go to the next page to find our eigenspaces. So let's find out our eigenspace for eigenvector 2. So lambda is equal to 2 as our eigenvector. We want to do that A minus 2I business and then find out the null space of this. So it would be 1 minus 2 is negative 1. 2, 0, 0. 1 minus 2 is also negative 1. And then 0, 0, 0. So we're guaranteed at least one dimension, well, exactly one dimension for our null space. And so if we reduce this, what are we going to get? If we find a null space, we say x2, xyz. Can we use xyz? It's 3 dimensions, so let's use xyz. So it looks like minus y plus 2z is equal to 0, and z is going to be our free variable. Y is equal to 2z, z, z. And then for the first one, we have minus x plus 2y is equal to 0. So x is equal to 2y, positive, which is equal to 2 times 2z. So that's 4t. So if you let z equal to t, your y is equal to 2t, and your x is equal to 4t. And so your null space is going to be t times 4, 2, 1. Is that right? Yeah, we're solving for this as if it was equal to 0, so we're finding the null space. And so the E2 is going to be equal to the span of this thing. And so your E vector is going to be 4, 2, 1. Okay? So we got one vector for this one eigenvalue. That's a good start. Now let's take a look at our second eigenvalue. Lambda is equal to 1, and hopefully we get a two-dimensional 2D parameter or two-dimensional eigenspace for this. Again, we start off with a minus 1 times I. So 1 minus 1 is 0. 1 minus 1 is 0. And then 0, 0. This is 1, right? 1, 2 minus 1 is 1. And if we row reduce, we can essentially eliminate the bottom. So it looks like we're going to have z. 2z is equal to 0, or z is equal to 0. And y is equal to 0 also. So x is a free variable. Is that right? X can be anything. So we have x is equal to, or not x. So I think we only get one vector out of this. Is that right? We force it to be. That's a bummer. So lambda is equal to 1. We only have one vector associated with this, which is t times 1, and then the x, the y, and the z have to be equal to 0. So it looks like this has geometric multiplicity 1. So that's not the same as the algebraic multiplicity. So all that stuff in the previous page is useless. Because I was trying to solve for the null space of this, find the null space, so I set these things equal to 0. I get z is equal to 0, and y is equal to 0, so x is your free variable. So this is like t 0, 0. So if we take the t out, it'd just be 1, 0, 0. And I only got one vector out of this. Because this had algebraic multiplicity of 2, I was looking for 2 vectors. But in this case, I only had one.
And what does that do with the problem?
That just means it's not diagonalizable. Let me see what the question for that. Maybe I picked the wrong problem. Determine whether A is diagonalizable. And if so, find a diagonal and find P.
So we did have 2 vectors, but then what was the next step?
Yes.
Let's just say the next vector was 0, 1.
Okay. So if we had another vector, then we found then we actually can say that it is diagonalizable.
Do we do anything else with that, or not?
Yeah. Well, the other thing we have to do is we have to find out, find the matrix D and find the matrix. We also would like to find the matrices P as well. So for this, when I say should work, it actually doesn't. So it turns out that, see next page,
So order that.
it will matter when we try to find the P matrices. See next page, A is not diagonalizable. Diagonalizable. Okay. So let's actually do one that is diagonalizable so we can see how those matrices. I wanted to do a 3 by 3 matrix, but I'm afraid to try the next one. Well, I suppose I can have Mathematica check real quick to see if it's diagonalizable, right? Let's put a reason here. It's not diagonalizable because algebraic multiplicity for lambda 1, which is equal to 1, is not equal to, I'm sorry, algebraic multiplicity is equal to 2, and it's not equal to the geometric multiplicity.
If you want a 3 by 3 that works, since your eigenvalues are just sitting on the diagonal, you could just
Change one of the eigenvalues.
And now you've got 3 different ones and it's passed over.
Too many zeros. I'm afraid of the zeros. Should we do that? So if I change this to a 3, you think that'll work? Let me still check with Mathematica. What do I want to check for? Diagonal matrix. Um, 3, 2, 0, 0, 1, 2, 0, 0, 2. True. Hey, we should check if this is false. False. So if it was a 3 in there, it would be diagonalizable. So we'll use that. Oh, what happened? All right. So let's find out if this is diagonalizable. Well, it is diagonalizable. Let's find the diagonal. Oh, it's right there, 3, 1, 2. Let's find the matrix P that would make this diagonalizable. So we know that this is diagonalizable because we had Mathematica check. But if we were to find out the eigenvector or values, we would find the characteristic polynomial. So that's a determinant of A minus lambda I, which is 3 minus lambda, 1 minus lambda, 2 minus lambda, and then there's a bunch of zeros so that everything else disappears. So we got 3 eigenvalues that are distinct. So eigenvalues are 1, 2, and 3. So let's find the eigenspace for the first one. So basically we should expect one vector out of this. And so E1, we need to look at the matrix A minus 1I and then find the null space of that. So 3 minus 1 is 2, 1 minus 1 is 0, and 2 minus 1 is 1. So if we want to find the eigenspace for this, it looks like Z is going to have to be 0. It's going to be forced to be 0. Our 2x plus 2y is equal to 0, so x is equal to negative y. And that's going to give us our, if you let t equal to y, then that's going to give us our parameter. So y equal to t. It's going to give us our vector negative t, and then t, and then z is equal to 0. So this is our eigenvector for your eigenvalue of 1. Now let's find the eigen space for 2, eigenvalue of 2. We do the same thing. A minus 2I is going to be, subtract 2 from the diagonals. That would be 1, 2, 0, 0 minus 1, 2, and 0, 0, 0. So that's gone. So from the second row, we have the relationship minus y plus 2z is equal to 0. So this can give us a z, be our free variable parameter t. So y is equal to 2z, which will turn into a t. And then we have x plus 2y is equal to 0, so x is equal to negative 2y, which is negative 2 times 2z, so that's going to be a 4t. So when z is equal to t, y is equal to 2t, and x is equal to negative 4t. So our eigenvector for this is negative 4, 2, and 1. So our third eigenspace that we want to look for is for the eigenvalue of 3. So A minus 3I. Subtract 3 from the diagonal, so you got 0, 2, 0, 0, minus 2, 2, 0, 0, negative 1. So with the last, we should work this out and reduce. If we reduce, the second row, it can disappear, right? Can it? Sure. I'll just cross it out. You know, if you row reduce, you can multiply you can just add the first two rows and then take this, multiply this the third row by 3 and then, or by 2, and then add it to the second row, and that'll disappear. So basically, you'll have z is equal to 0, y is equal to 0, and then your free parameter is x. So your eigenspace is going to be spanned by 1, 0, 0. Okay? So you have you can have your diagonal matrix look like this, a 1, 2, 3. But it turns out that you can also have your diagonal matrix to look like this. And if you know about permutations, you can figure out how many other diagonal matrices you can come up with. How many total diagonal matrices can you come up with? Just for fun. 3 options, 3 slots, can't repeat. No, close. D3 factorial. So there's 6 possible diagonal matrices we can come up with. Let's just call this D1 and D2 and see what the difference is between these 2 diagonal matrices. Okay, so we know that this is diagonalizable, and we have these diagonal matrices. But if it were diagonalizable, right, then, oops. If it were diagonalizable, then there's supposed to be a relationship between the matrix A and these 2 matrices, right? They're similar. They're similar, but the fact that they're similar means there is an invertible matrix that can make this transform into D. So what that means is that we should be able to write 3, 2, 0, 0, 1, 2. This is a 1. 0, 0, 2. That means that we should be able to find an invertible matrix P so that this equation will be true. It also means that we should be able to find well, this is where it'll be different. So what happens is that if you have 2 matrices, or if you have 2 possible candidates for the diagonal matrix, well, not possible, these actually are diagonal matrices that are similar to A, then if these 2 matrices, D1 and D2, are different, then they must be different invertible matrices to transform this A into this diagonal or the second diagonal. So now the question comes in, what is P and what is Q? right? We should be able to come up with these matrices. Well, what is P and what is Q? It turns out that P and Q are exactly the eigenvectors. You have to use all three of them, yeah. It's exactly the eigenvectors. Now, we found three eigenvectors, right? Each corresponding to an eigenvalue. So what do you think is going to make P and Q different from each other? The what? The order. It's the order of the eigenvalues. So let me write this down here and then copy it over to the other page. Let's call this V1 to be the eigenvector for the eigenvalue of 1. We got that to be negative 1, 1, 0. V2 is negative 4, 2, 1. And V3 is equal to 1, 0, 0.
Sorry, I'm confused. You found vectors in the null space,
For each of these eigenvalues.
but that technique, can't it end up finding like a vector that's flipped the other way or that's twice as big? Or don't you do some kind of scaling to make all this work? Because like, you know, that could have been 1 minus 1, 0, right? That would work just as well for the null space for E1. And at the end, it could be 2, 0, 0. So there's different eigenvectors that work. So somehow you have to find the one that matches the, I don't know.
I
don't know. I don't remember seeing this, but it just suddenly occurred to me that
Yeah,
process of
that's a good
finding
point.
the null space has some amount of randomness in it.
Yeah, it does, because we're just saying T, and we're just assuming T is equal to 1, right?
What percentage of X be independent?
They have to be linearly independent. Well, these will be linearly independent because that was one of the theorems that we had. But does it say anything else about what the eigenvectors should be? Well, let's try it. Let's use mathematical to multiply out.
Maybe it doesn't matter, but it seems like it should matter.
It seems like it should, right?
Or maybe if you put
But
it
if it's scaled by something,
oh, you know why?
then the inverse will
Maybe
unscale it. Yeah.
Maybe that's fine.
Yeah, so that's why. Yeah, that's why it doesn't matter. All right. Well, let's take this information that we have, so this is the information that we got last time. And so this is where we would say that the order matters. For D1, maybe I should actually, instead of just putting D1, put the actual matrix D1 here. D1 is 1, 2, 3 in the diagonals. So the P matrix that would make this work would be the eigenvalue for 1 is in the first column, so we're going to use the eigenvector that's associated with that eigenvalue, negative 1, 1, 0. Eigenvalue of 2 is in the second column, so we'll use the eigenvector associated with that to be the second column, minus 4, 2, 1. And then the eigenvalue of 3 is in the third column, so we'll use the eigenvector associated with eigenvalue 3. That would be 1, 0, 0. So this would be our vector that that should be invertible, and this vector should be a vector, or I'm sorry, this matrix should be a matrix so that when we find its inverse, multiply it with A, and then multiply it with itself, should give us this diagonal matrix. For D2, we decided to put D2 in a different order. Three, 1, 2 instead of 1, 2, 3. And if we do it that way, our Q vector, the invertible matrix that's supposed to make this into this similar matrix, should be the eigenvalue of 3 is in the first column, so I'll take the eigenvector associated with that eigenvalue. And then 1 is next, negative 1, 1, 0, and then 2 is the last one, so that's negative 4, 2, 1. So these are your invertible matrices that would invert this, that would take this matrix and find a similar diagonal matrix in this particular order. Okay? Should we actually check with Mathematica, or should we just move on? What? It is invertible. So we can find the determinant of these matrices to make sure it's invertible, and then the last final thing to check is to take the inverse of P, multiply with A, and then multiply with P. You should get this 1, 2, 3 matrix. Okay? All right. Is that good? We don't need to see it worked out? You'll just trust me? Oh, I hope I'm right. I hope I'm right. Okay. So that's the idea behind being diagonalizable. There's an interesting problem over here in the book that has K stuff again. Remember that K stuff?
Oh, yeah.
Let's do one of these problems.
God help me.
Should we just stick with a 2 by 2 matrix?
Like an arrow. Oh, whatever.
I don't know, 24, 25, 26? Let's do 24. All right. Find real values of K for which A is going to be diagonalizable. Oops, sorry, what happened? So we want to find the eigenvalues, then find the associated eigenvectors and stuff like that. So let's start off by finding the characteristic polynomial. So this would be 1 minus lambda, 1, 0, and this would be K minus lambda. So this is 1 minus lambda, K minus lambda. So we got the eigenvalues to be 1 and K, right? So at least to begin with, we want to make sure that K doesn't equal to 0, because remember, if K was equal to 0, then it's not going to work out for us. But we want to know if this is okay if K is equal to 1. So let's see what happens. Let's find the eigenspace for K. So we do that by finding the null space of A minus Ki.
So why does it not work if K is 0?
Then we have an issue with an eigen. If we had an eigenvalue of 0, then it's not invertible.
Well,
Then
we're not trying to invert A, though, right? We're just trying to find an invertible matrix that diagonalizes. Does that mean it's not diagonalizable?
yeah, I think it just means it's not diagonalizable. All right, now maybe I should think about that.
But it said like if they're similar, then their ranks are equal. That suggests that they can have some rank other than full.
Other than the full rank.
So that suggests that two matrices can be similar if their determinants are 0. Just a question.
All right, well, I'll keep that in the back of my head, and we'll see what happens. Okay, so we're finding the null space of this thing. You got 1 minus k, 1, 0, and k minus k. So we have the relationship 1 minus k times x plus y is equal to 0. So if we set a free variable y is equal to t, x is going to equal to, what's this going to equal to? Minus t over 1 minus k. So it looks like we might have an issue when k is equal to 1 as well. So your eigenvector associated with this is going to be 1 over 1 minus k and 1. I don't know if we need to do this, but let's find E1. So this
Is that supposed to be a null space?
this is the null space, yeah.
That doesn't look right because you're going to get 2 in the top column. Oh, you got a minus sign that's missing there.
Oh, this.
Yeah, that works.
Okay. All right, so A minus 1I, the null space of that is 1 minus 1 is 0, 1, 0, and this is k minus 1. So what's this going to be? Jeez.
It's just 1, 0. You knock out the bottom.
Oh,
row,
yeah.
Right? So eigenvector 1.
So y is going to have to be equal to 0, and then x is your free variable. So there. Okay. So k cannot equal a 1. Because that would make that undefined, and that would make this multiplicity 2, and probably would give you some issues with finding the null space of this E1. And then that's it, right? Now I want to put k is equal to 0, but then Hal's got me thinking now why that.
Why would you not?
Because I was thinking if k was equal to 0, then this is not invertible, but a doesn't matter if a is invertible or not. You can still find a diagonal.
So if k is 1, then that left matrix has the same eigenvector as the right matrix. Right? So
Yeah,
that's what
yeah, and so you'll those vectors would be linearly dependent, so it's not going to work. So when k, we want to say k does not equal to 1. So what happens if k is equal to 0?
Do you think it's 1, 1?
If k was equal to 0, it's negative 1, 1. That's linearly independent, so I think that'll work.
yeah, you get 0, 1 for that.
Yeah. So it turns out, yeah, it looks like k equals 0 is okay. It just means that a is not invertible, so that's what I was worried about, but we don't care about a, we just care about it being diagonalizable.
We could check.
Yeah, well, I was trying to check in my head as we were working through the problem. Then your a is equal to, if k is equal to 0, your a is equal to 1, 1, 0, 0. And the diagonal would be 1, 0. And then if we work through this thing out, your matrix P would be, the first column would be 1, 0, and the second column, if k was equal to 0, would be negative 1, 1, which should be invertible, right? Because the determinant's not equal to 0. What's the inverse of this, real quick? 1 over the determinant, and then you switch the diagonals and negative the wings. Yeah, so it'll work. So this is the only restriction. So for this A to be invertible, we want to just make sure that k is not equal to 1. Or not, what did I say? For A to be diagonalizable, we have to make sure that k is not equal to 1. All right. Let's take just a quick look at the last couple of theorems in this section. Couple. So here's something that we kind of, well, Federico also mentioned that if A is diagonalizable, then your eigenvectors are linearly independent. Okay. So it turns out that you have, if all of your if you have the same number of eigenvalues, distinct eigenvalues as the size of your matrix, then the eigenvectors are all going to be linearly independent. So the only issue that we would have here is that if we had an algebraic multiplicity of greater than 1 for one of the eigenvectors, then we might have an issue with this. But the theorem says that you should get n linearly independent eigenvectors. Okay, we won't prove that. The next theorem that comes up has something to do with the basis for the eigenspaces. If you have k distinct eigenvalues and B sub I is a basis for the eigenspace, then if you collect all the bases, then you're going to have a linearly independent set.
Now, is that a basis of one of the eigenspaces?
Each BI or B1,
You're putting them all together.
yeah.
Okay.
So it's the union of all those. It's going to be the basis. So I don't know if we came up with an example of an eigenspace that has that's two-dimensional. I don't know if we ever did that. And I wish I could come up with one real quick off the top of my head, but I don't think I can. But this kind of confirms this idea that if we had less than, if the number of eigenvalues you have is less than the dimension of your matrix, then that eigenvalue that has more than multiplicity of 1 will have linearly independent basis that's also linearly independent from all the other basis for the other eigenspace. oops, I want to keep this all on the same page. If A is a matrix with n distinct eigenvalues, then you're automatically diagonalizable. So we didn't prove that, but we showed that in one of the problem that we were messing around with, where we changed one of the eigenvalues to 3 so that it's all different. Then if you have distinct eigenvalues, then it's automatically diagonalizable. If they're not distinct, right, then there's still a chance for it to be diagonalizable. It depends on the geometric multiplicity agreeing with the algebraic multiplicity. And then the last theorem has a preceding lemma. And without proving these things, all these theorems and lemmas are essentially saying the same thing. I think to get through the nuts and bolts of it, we should actually prove it, but we're not going to. So this lemma says that if A is an n by n matrix, then the geometric multiplicity for each eigenvalue is less than or equal to its algebraic multiplicity. And if we want it to be diagonalizable, then the eigenvalues with geometric multiplicity, algebraic multiplicity bigger than 1 will have the exact same geometric multiplicity. Okay, and the examples that we've come up with where the algebraic and geometric multiplicity aren't the same, for us the algebraic multiplicity seems like it's, or the geometric multiplicity is less. And so if we find an example where the geometric multiplicity and algebraic multiplicity are the same, then we can say that that particular matrix is diagonalizable. All right. Guess I really should come up with an example like that. So maybe I'll come up with an example like that and then show the algebraic multiplicities and the same geometric multiplicity is the same. I think that's I think that's it for this chapter, or for the section and for the chapter. Rami?
So that was just saying that the geometric multiplicity is always less than or equal to algebraic multiplicity?
Yeah, this lemma is saying that the geometric multiplicity is always going to be less than the algebraic, less than or equal to the algebraic multiplicity. But if you want it to be diagonalizable, then it has to be equal.
Is it referring to like the total number, like the total geometric amount of algebraic multiplicity, or is it for each eigenvalue?
The total.
The total.
Well, if you look at for each eigenvalue would have the algebraic and geometric multiplicity.
And that would vary.
Possibly. Yeah. So without dealing with an actual matrix, let's say matrix A has a characteristic polynomial that looks like this. Lambda minus 1 to the third, lambda plus 2 squared, and lambda minus 3. So let's say this is a characteristic polynomial. So lambda is equal to 1 has algebraic multiplicity of 3. Lambda is equal to negative 2 has algebraic multiplicity of 2. And then lambda is equal to 3 has algebraic multiplicity of 1. Right? So if we go through this work from here, so there's going to be a lot of different cases. So suppose we have the eigenspace of 1 had 2 vectors. Then what can you say about matrix A? It's not diagonalizable, right? So if it only has two vectors, then what you're saying here is that the geometric multiplicity is equal to 2, which is less than 3, but more importantly, it's not equal to 3. So in this case, A is not diagonalizable. Okay? So suppose E1 has an eigenspace V1, V2, V3, and E negative 2, the eigenspace is going to be spanned by x1 and x2. And then if you have algebraic multiplicity of 1, you're pretty much guaranteed an eigenvector for that. So if you have this, where the geometric multiplicity is agreeing with the algebraic multiplicity for each of these eigenspaces, then we can say that this is diagonalizable. Okay? Not only that, but the other theorems preceding it says stuff like V1, V2, V3, X1, X2. And then if we found the eigenvector for this, let's say this has an eigenvector of U. What can you say about this list of vectors? They're linearly independent. Okay? Because the whole collection of all these eigenvectors should be linearly independent. And what can you, if this is supposed to be our matrix A, and say matrix A was invertible, so it has all these eigenvalues and eigenvectors, what can you say about the dimension of A? It's a what by what matrix? 6 by 6 matrix. So these vectors should be 6 vectors each. And then we were talking about a 6 by 6 matrix. All right? All right, next time we'll jump into a couple of sections of Chapter 5, and then we probably should start thinking about the final exam. So we'll start talking about the final exam on Monday.